तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everyone. With this lecture we are starting a new series of lectures on the topic of digital VLSI system design. This VLSI has been a very popular word of late. Almost everyone talks of VLSI, not necessarily technology, people with technical knowledge. I can say it has even become a household word. And you find newspaper articles in science section on VLSI. So, what is all this VLSI we will see in a while, and in this series of lectures what are the things we are going to learn, that also we will see. But you can also see in the title the lecture is not simply VLSI system design, it is a digital VLSI system design. So, first I need to explain to you what is digital system design is. Of course, this is again an advanced course as far as digital system design is concerned. We have earlier lecture series on digital system design basics. But for the sake of introduction, all electronic systems have two types of components. One is analog, the other is digital. With the advent of digital computers, it was easy for people to process signals in a digital domain. An electronic system essentially processes signals. What is a signal? Signal is any variation of a quantity with respect to time. So, for example, we can monitor the temperature, or even the speech that I am now giving is a signal, because there is an amplitude variation with time. So, these signals can be earlier in the analog domain. For example, we had a simple system of microphone, amplifier, speaker, standard PA system, public address system. These signals will be taken as it is by an amplifier, will be amplified and then delivered to the speaker. Such a process is called analog signal, and analog signal had a few things which are not very friendly. One is this signal varies continuously in time and continuously in amplitude within given limits. So, in order to store this and reliably reproduce it, it becomes difficult, because we do not know how reliable the stored signal is when you take it back. So, we need capacitors in which the signals, the values, the amplitude, instantaneous amplitudes are stored. How many such capacitors will you use? All those things become a problem. So, they went to what is known as discrete time signals, where instead of storing the signal at every instant of time, you do it at discrete intervals of time, and it is possible to reconstruct them. Let us not go into the theory of communication. It has been proved that with samples of a signal taken at frequent intervals, one can reconstruct the signal in full without any loss. If it, using this principle, one could store the discretized time signals at discretized time intervals, this is called discrete time signals. And there again you have the problem of amplitudes. What is the amplitude stored, and when you read that amplitude, whether the amplitude has been corrupted either by an external noise or by a leakage. So, we went to a third possibility of discretizing the amplitude also. When you discretize the amplitude, what happens is, we do not at every discrete time we have a value, but we do not store the value. We store the value, we only have given fixed values, and the nearest value to the amplitude at that time will be stored. That way there is a limit, there is a variation allowed in the signal storage. If a signal leaks by a small amount, it does not matter, or the signal picks up a little noise and the weight does not matter, because these levels are discrete levels, and within those levels, as long as the signal resides within that level, becomes easy to reproduce it. So, storage and reproduction and transmission of digital signals are much easier compared to analog signals. The second thing is, I want to improve the accuracy of a digital transmission or digital system. I need many more stages. You see, in analog also we can improve the accuracy. An improvement of accuracy in analog is an exponential process. The difficulty level, the complexity level involved in improving the accuracy of an analog system is much more difficult compared to digital system, where all you have to do is to replicate. If you have more hardware, you can have more accurate signal. If you have less hardware, you can have less accurate signal. So, the implementation point also, digital signals becomes easier to handle. These are the reasons people went for digital, and when the advent of computers, it become very easy. All you have to do is to transform a signal to digital domain. Once you transform signal to digital domain, they become numbers, mere number representation. These numbers are handled by the computers or digital signal processors, and then after the manipulation, again they are given out as numbers. Those numbers are converted back into signals, and those signals are displayed or stored or transmitted. So, that is why digital has taken an enormous importance in recent times. But we should not forget that analog is also equally important, because most of the naturally occurring signals are analog signals. As I said, speech, a person's speech, audio of a music or instrument, video signals, any variation, any parameter that you want to monitor in a system. These are all analog variations, and analog variations have to be discretized both in time and frequency to get digital signals, both in time and amplitude to get digital signals, and which can be processed. So, there is a little bit of analog processing involved in any system, but now the trend is more and more digitized. So, now this order of about 90 to 95% of all signal processing in electronics is digital domain. The remaining 5 to 10% is analog domain. But the difficulty in those 5 to 10% is almost matched to the difficulty of this 80 to 90%, both in terms of the cost in the design and the time involved in doing this properly. Of course, we have now circuits in which both digital and analog reside simultaneously. These are called mixed signal processing. So, there is a wide popularity and wide activity, a large activity in digital system design, and that is why we are concentrating on digital system design. Of course, you need to know analog also if you want to become a complete VLSI designer, but no one single person can be an expert in all the fields of VLSI. VLSI is a large field, extensive field. So, one can concentrate on signal processing, digital aspects design, somebody can concentrate on analog aspects of design, somebody can concentrate on the layout, somebody can concentrate on tools for VLSI design, somebody can concentrate on improving the power performance, etc. So, in this course, as I said, we are only concentrating on the digital design aspects of VLSI systems. Now, let us take the second point, namely VLSI. What is VLSI? Why is it so important? This is again a historic evolution, mostly because of technological advances. Earlier days, early 50s, we had the transistors. Early 50s or in 50s, we had the advent of transistors and Bell Labs. A single transistor was invented, used in applications such as amplification, And then when people wanted to make systems using transistors, they had to build a circuit with a transistor, resistor, capacitor, discrete elements. They have to be wired up, they have to be connected, soldered, whatever. Then they thought of more complex systems with more transistors, a couple of transistors, make a digital differential amplifier, all of you know that, or many more transistors in many circuit applications. And doing all these interconnections, there are a couple of problems. One is the matching. I would like to have the characteristics of these transistors as near, as close to them, as close to each other as possible. When they are fabricated, manufactured over different processes, different times, different yield, different times, different lots, the matching of these characteristics of these transistors become a difficult job. Whereas when you can fabricate a few transistors, manufacture a few transistors together all in one single process on a single crystal of silicon, it is more likely that the characteristics match. Second thing is interconnection. I have transistors, resistors, capacitors, all those to be integrated, connected. The reliability of the connection, when it is done in a chemical processing, as you fabricate the device, as you manufacture the device as a process, is much more reliable compared to taking these devices externally and connecting them. So the integrated circuits became very popular. What is an integrated circuit? A circuit which is integrated to a single silicon crystal. All the components, transistors, resistors, capacitors, etc. But then they found it difficult to make capacitors. It takes more area, and the reliability of the value of the capacitance was not that good. Resistors is less complex than capacitors, but still more complex than transistors. So they make all sorts of changes in the design to have as many transistors and active devices as possible in a system, and have very few resistors, and if possible eliminate capacitors completely. So this type of circuits became popular. These are called integrated circuits. And about 10 years into the evolution of transistors and discrete transistor circuits, in the early 60s, integrated circuits became very common, where simple transistors were connected together along with other things, all in one form, in one single wafer, one single silicon crystal. And then once you have a technology of making things together as a complex circuit, we have so many applications, so many complex requirement of systems. People started experimenting, and I can make a transistor amplifier or a differential amplifier or a simple PLL or a simple TTL gate using an integrated circuit. Can I push this further and make a bigger systems? Yes, of course. So people started pushing more and more as the technology advanced, VLSI technology. The amount of money spent on research and creating infrastructure in VLSI grew enormously, and we went to the stage of microprocessors. In the early 70s, entire 60s, integrated circuits of different description, multiplexers, memories, all those things came into picture. And then early 70s saw the advent of microprocessors. What is a microprocessor? Microprocessor is nothing but a CPU of a computer, central processing unit. All of us know any computer will have a central processing unit, and you have to make it as a computer by using the central processing unit along with input-output devices, memories. Now, in order to build this central processing unit, earlier they used to have discrete components. They used to buy an arithmetic logic unit, and they had to have this arithmetic address unit, all those things connected together. Then they thought, if I can put all of them in one place, in one silicon wafer, it's not even called a wafer, silicon die, then it is possible to make these interconnections very simple, reliable, and the speed increases. See, the advantage of the integrated circuit is many. Advantages are many. One is the cost. Because we are going to make a batch fabrication, the cost is shared by all these devices. Of course, there is a development cost in the initial development cost, but then as you make more and more of these devices, as you fabricate more and more of these devices, the cost gets shared. reduce. I already told you of the reliability. When things are connected internally in a silicon bonding process or a chemical process, the connectivity is perfect. Whereas when you connect this externally, you have a loose wire, dry solder and things like that. So cost cuts down drastically, the connectivity increases, reliability of connections increases, the power consumption also decreases, because we power up the whole thing with a single power source, and then the power dissipation decreases. All the advantages that you want to have, speed also increases because they are so close to each other, and you can design very fast access devices. So all the things that we wanted to have, high speed, low power, low cost, all those things can be achieved in integrated circuit. That is the idea. That is how the technology was pushed into larger and larger circuits. And of course, we have to compliment the VLSI designers, VLSI system designers and VLSI technology people who came up with all these things. That the designers wanted this, the technology people provided that. So microprocessors, early 1970s, 1972 was the time when 8080 was the most popular microprocessor all of us are familiar with. Intel 8085 8-bit microprocessor came in 1972, which is being used even today in instruction all over the world. Many books have been written. And then digital signal processors became a new family of device processors. The difference between microprocessor and digital signal processors, in the sense the digital signal processors have some specific functions that can be performed with them, which are not possible using microprocessors. Like there is a hardware multiplier. A microprocessor may not have a multiplier. Even if you have a multiply instruction, it is performed by some sort of a microprogram, whereas a digital signal processor is a hardware multiplier, and has other features like hardware, Harvard architecture and all that. I will not go into the details of digital signal processors, but as the technology improved and lots of signal processing requirement came for digital system design, in many household, many appliances, both industrial needs, commercial needs, domestic needs, household, military, DSP, digital signal processing, became a very standard tool. It was there all along, but there was no hardware, there was no electronics which you could do these things very efficiently, effectively, in a cost effective manner. The advent of this VLSI technology, DSPs became affordable for many applications. For example, people thought of designing hearing aids, people thought of designing chips for cell phones, people thought of designing so many other gadgets, and then that developed into digital signal processor alone can only do so much, but then you want to make it as a digital processor into a useful device, into a useful application. You can make what are known as application specific integrated circuits. DSP or digital signal processor is a general purpose processor in which is something similar to microprocessor. It has lots of features which are common to microprocessor, features which are different from microprocessor for signal processing applications, but they are still programmable. Whereas ASICs are application specific integrated circuits which came about in 1990s, these were processors, application specific integrated circuits. These were specific ICs like a hearing aid, like a cell phone, like even a simple device like a controller for a TV or a washing machine. Anything which is specific to that application and it cannot be used for any other application became an application specific IC. This application specific IC concept became very popular when volume sales was very important. You want to make a cell phone, at least if you sell 1 million, 2 million pieces, only then it is worthwhile, because you need to have an initial cost and the system cannot change, the performance cannot change once the program is fixed, the design is fixed. So you have to go in for volume production. On the other hand, we have another complementary part of this called FPGAs, field programmable gate arrays. Field programmable gate arrays are similar to DSPs in the sense they are programmable, but they are not DSP. The analogy stops there, programmability, but these are specific functional. As again DSPs, microprocessor is DSP is a evolution of a microprocessor for signal processing applications. Microprocessor is used for more as a data processing applications like database, huge commercial type of computers. Whereas digital signal processor was used for signal processing, which is most important thing in say filters, FFT and things like that. So in that sense microprocessor and DSP have a commonality. Similarly, DSP, FPGA and ASICs have commonality in the sense they are functional related, but then DSP is a programmable which can be used for different functions, whereas FPGAs and ASICs are meant for a specific function. So it has the advantages of ASIC and the advantage of DSP, the programmability of DSP and all the features, the architectural features, innovative features of a ASIC, both put in FPGA. So FPGA became a very widely popular, very popular device for prototyping or small scale application, universities for example, research. For example, in this course we will see extensively the use of FPGAs. All the applications, all the examples we will talk about, we will use FPGAs because we cannot make an ASIC, application specific IC for every application we are going to teach you in this course. That means you have to go to your nearest foundry, make it into and bring it back. Whereas FPGAs are available, there are software tools, you develop the program and the software tools, download into the FPGA which is available on a board, then you can run it and test it for your design is correct and all that type of thing. And then finally the concept is now evolving more and more system on a chip. That means the entire system, like a computer is a system, we have a memory, I/O, any peripheral like serial I/O, DMA, or it can be even systems such as digital camera, complete MPEG decoder, this MP3 player. They talk so much about all these different devices today, all of them in a single chip so that it can be put, for example digital camera, it looks so small, tiny, one chip has everything in it. So this is called system on a chip. It is also called embedded systems. People say embedded systems today, these are embedded systems and nothing but systems on a chip, a single system in which, single chip on which the whole system is integrated. So that is the evolution, and what we will see in this course is how to design. This is the design basic in a university course or any program, any course or any university program for that matter. You cannot go all the way to a system on a chip. Just as you cannot in a digital system course, you cannot design a computer in a digital system design class. But I can tell you all about the fundamentals, what are the various basics involved. Similarly, we will touch upon various aspects of signal VLSI design and how individually things can be designed so that as you go into a workplace and with all the tools available to you, you can put them all together, and of course nobody does no single person designs a microprocessor. It is a big team of people working for several years coming with a microprocessor. So you will have to contribute your share. Likewise, if you know everything about everything, then you will be part of a team to all put together a microprocessor or a DSP or an ASIC or FPGA based system. So that is the intent or objective of the course. So a few things I have more or less touched upon the need for this course, and we will now talk about what we will learn in this course in detail. Before that, a few things I would like to talk about this IC itself. As I said, IC has become a household word now. We will tell you a few things about it, how it became. Now, this VLSI technology fueled the whole thing. Because of the technology, there is advances of this VLSI used in communication computer control application. Earlier these were, see, none of them is new. There were communication applications, but people had to design huge equipment, radio, there was radio links, in transmitters were there, receivers were there, in military applications the radio links were there, radar applications were there, even World War. But these are all huge equipment, very big, very power consuming, very expensive, sometimes unreliable. Now all these things are brought smaller and smaller and smaller. Along with that comes the affordability, the reliability, power dissipation, everything improves. So today we have an explosion of VLSI in communication. We already said about these internet applications, all of you know, cell phone, how many different things we do. Of course computers, you know, the evolution of computers from 8085 and 8086 all the way up to Pentium process today. control applications from starting from simple control of in a washing machine or a mixer at home to control aircrafts, missiles, you have explosion. And as I said, as you grow in the scale of either from 885 to P3 or from a simple washing machine control to missile control, it is an evolution which is complex design, performance is demanded as higher, we want to do it faster and less area, less cost, less power, everything we want. We want to spend less money, we want to dissipate very small amount of power, we want to make it as tiny chip so that you can hold it in a small device and put it in your pocket like a cell phone. People have a hearing aid within, which is almost within inside the ear, we do not even know that person is having a hearing aid, that type of thing. And the performance in terms of what it can do today, amount of memory it has and the type of processing it can do, all that complexity increase. So that means we have challenges in design, we have challenge in application, we have software. Design has to be done before you can really put it into a chip, and then once you make a chip like a DSP or a microprocessor, you should find a use for it. Nobody, you cannot sell 1 million pieces or 10 million pieces of a DSP if you do not tell people how to use it, where you can use it. And then more important is software. We cannot do hand design of all these things. EDA means electronic design automation. In electronic design automation, software is required. Without that software, you can't do these things today. Everything is done in a computer. Computer designs VLSI chips. This is simple statistics, you do not have to be very serious about this. Of all the equipment today, about 30% of semiconductor component, which is, I think even this is a very conservative number, it is increased, I think. And application specific ICs are very much used. We are talking about $4,000 million of ASIC design, or 300,000 different ASICs. There is a feature size which I do not want to go into great detail here at this point in time. It is a VLSI technology related thing. How do you make it all small? How are you able to make a small piece of tiny piece and put it as a cell phone and put it in a pocket? There is a battery there, there is a memory there, your cell phone is there, everything is in such a small device, looks like a snuff box, put it inside, you do not even know that. In fact, there are people take cameras into conferences and photograph you without your knowledge. How is it possible? Because of the tiny nature. That is because the feature size, as they call it, shrinks. Connecting a device to another device using a wire, or within a device design a transistor, for example a base, a collector and emitter, or a MOSFET with a source, drain, gate, channel, substrate. The size has to be very, very, very small. If I am going to accommodate a microprocessor which is equivalent of several thousand transistors, each of these transistors will be very, very, very tiny, like a memory, for example. If I have a memory of gigabits in a small area, each memory cell which contains several transistors has to be very, very small. That is what we mean by feature size. We will not go into the actual definition of feature size here, but you have an idea. And that is 0.13 micron was in 2000. In the year 2007, which are talking about 0.07 micron, which is talking about nanometers. 0.7 micron means 17 nanometers. 17 10 power minus 9 meters is a type of length, and how this means the technology which requires electron beam technology, electron beam lithography, molecular lithography, so many things, so much advances. But we are not going to design only design, so we are not worried, but then somebody is going to fabricate it, that person has to worry about this. And we are talking about 16-inch wafers, 16-inch diameters wafers. You can imagine the size of 16-inch diameter wafer, no? 16 inches is so much. You put that huge plate like this, 16 inch, huge plate. And that wafer I make a device which is very tiny, so I can make millions of, at least thousands of these devices in this wafer and scribe them into individual things and package them. So this is to give you an idea, this is all. You do not have to memorize these facts, but this is an idea, common sense idea, to just know what we are into today. And what is the application area? I said we can almost anything. Today there is nothing that is not application. VLSI application. Telecommunication, that is what we said about telephones, cell phones, radio, networking, internet. Internet is a lifeline today. Your computer network down, then you feel as if you lost something. High performance computing, multimedia, everybody wants to make a projection of PowerPoint and things like that. Industrial controls and robotics, I already talked about very simple things, robotics, automatic robots, missile technology, automotive. Your car has so much of IC design, IC parts. Today's cars has so much electronics, and if ever electronics is made as a big system, then you won't have a place to sit, and it will be huge systems projecting. Your radio, for example, car radio. In that noisy environment, you are able to listen to radio perfectly without noise. What is electronics involved, and what will be size it will take? Very small, tiny, because of VLSI. And emission control, brake control, everything is almost electronic. Energy management today is a major topic. Today we are energy starved globe. Even advanced countries have power outages. And one technique is to improve the power generation, which we are doing, but the other technique is to manage it properly. Like water and energy, we are wasting. We don't have water, but you waste it. Similarly, we don't have energy, but we waste it. How do you manage energy? So we need systems which can monitor and efficiently use it. Medical electronics, we have implants today, electronic implant. There are automatic insulin dispensers which can be embedded into our system, into our body, implanted into our body. Defense and space electronics, you can imagine the type of missiles even India has, but you can imagine the type of things the advanced countries will have. Defense electronics. Today nobody goes to the field to wage a war. We are done by electronically. From a ship anchored in the middle of the Gulf, you bomb a target very precisely in a country to destroy it without coming in the way of hazard. Consumer electronics has already told you enough. Television, everything consumer electronics today. MP3, DVD, whatever it is called. There are so many, you youngsters will know much more than me about these things, home appliances and electronics. So that is the reason why we have to read this, and I already told you about the evolution, starting from transistors from 50s to system on chip 2000. That is why today VLSI has become suddenly a buzzword. It's not that today it was invented. Electronics was there, applications was there, individual application transistors were there, but then putting together make it affordable. Once it becomes affordable and becomes a common, reachable by a common man, people start taking interest in it. TV advertisements come, newspapers start about it, and then you want to know what it is, and then we could become an important person, so people hire you. All these things I already told you, we have three things we have to do. Fabrication technology, it has advanced so much. We have de-linked design and fabrication. We have advanced CAD tools. Without CAD tools you can't do this. Computer-aided design tools for design. Design and fabrication are de-linked. I am not going to talk about design fabrication in this course. We don't have to know. You can't be anything, everything in this. VLSI is such a complex, vast field. You can be a designer, you can be an analog designer, you can be digital. You can, in fact, go to such an extent, you can be a memory designer, like that. This is something I already told you. The number of transistors, the size is shrinking. This is a law called Moore's law. As the years grow, about every 18 months, the number of transistors we can put in the same space doubles, whereas the productivity doesn't increase. That means I am able to give a larger design, but we cannot make those larger designs in terms of fabrication technology and in terms of the productivity use of that. The gate count, as I said, same Moore's law applied, 285,000 gates. A chip which ideally had 1997, the same chip can now be fabricated 10 million gates in 2003. And gate is few transistors, all of you know that, a simple gate, at least about 10 transistors in it. So you can imagine about 10 million into 10, 100 million transistors in a gate, in a chip. We are now reaching 1 billion. Everything, information revolution today, most of our access information will come through VLSI systems. Everything here in this diagram is familiar to you. There is this cell phone, there is this copiers, cameras, simple aerospace control, automatic robo. We have this even simple things like traffic light control, aircraft, everything, almost everything. There are lots of things you have to do. The fabrication cost is rising, but you have to keep it low because people will not buy if it is expensive. Manpower shortage is there, that means you have to have very good engineers to design these things. The electronics market is shifting to consumer. Consumer market is the only place where there is money. That is why every multinational. Why is every multinational interested in India and China? Because we have people who can buy these things. The number of people in these two countries, if they buy, even a small percentage of these people buy their things, they will be much more profitable compared to what they can sell in the entire United States or Europe. That is why. So market is shifting to consumers, and they sell you things which you don't need. You have to be careful. And then the complexity of the design is soaring. At the same time, manufacturing capability is increasing. TTM means time to market. You have to beat your customer. Everybody thinks of the same thing at the same time, but then you have to be, if you want to make your product more well known, you have to beat your competitor to that. So in this course, what will we read? We will quickly go through the content of this course. Introduction to VLSI design, that is what we did. But then we should know the design first. If you want to do VLSI system design, we have to know a digital system design. And as I said, this is a second course in this system. This is not a first course. Do not expect in this course don't expect us to teach you how to design a simple gate based structure or a counter or a adder or something like that. A first level digital knowledge is assumed. But we will do system design in this course, multiple input, multiple output systems. We can do it using multiplexers, using control programmable elements such as ROM, PLAs, PALs. We will do sequential design using and we will talk about setup time, hold time. These are important when you talk of design of VLSI. And we will do sequential circuits of applications for pattern generation, for example, pattern detection, for example, Moore-Mealy circuits. We can do any of these things using ROMs, we can do multiplexers, we can do PAL, and we will also do full system design. We will take a vending machine, for example. We will take a traffic light controller, for example. We can take a dice game, for example. How do you start from specification? How do you break it down? Specification to functional units and control units. And functional unit, how do you break it down to individual components? Control unit to find out what are the signals required to be given to the control unit, what are the signals that will control unit gives output. This will depend on the system. The system will give the status information back. How do you do that? And then from that you draw the ASM chart. From there you do the individual design of the controller and implement it using a ROM and a multiplexer or a PAL. All that will be done in this course. That is an introduction. So first you should know how to design an ASM chart. What is an ASM chart? Algorithmic state machine. It is nothing but like a flow chart in a hardware sense. How many clock cycles will it take for this to do this operation? From here, what goes next? What are the inputs that will be decided at this state? If the input is this, what will happen to the circuit? If the input is that, what will happen to the circuit? So such a detailed representation of the controller is called ASM, algorithmic state machine. ASM stands for algorithmic state machine. So in that we will give you several examples, as I said, bus orbiter, traffic light controller, dice game. And you can also do the whole thing by microprogramming. You can do two ways. As I said, you can do muxes, ROMs, and PALs, or you can do a microprogramming approach. All that we will see in this. That means it is a revision of a digital course in one sense, but in the second sense, or a more important sense, it is an advanced digital design course. That will be the first part of this course, first part of this lecture series. About 50 lectures will be there totally in this. Out of this, first part will be all this covering your basics. Then we will introduce you to how to start doing design using VLSI. For that, first thing you should know is how to represent this. As I said, this is all computer aided design. We don't do it by hand. That means you should represent your design in a computer. That means you need a computer language in which you can describe your design. Such a description is called hardware description language. HDL stands for hardware description. So we have to develop a hardware description language. This was the key thing. Your design on paper brought into a program which can be compiled and mapped onto a device which is available to you. This bridge is the hardware description language. It is a very key component that made the design efficient and fast. Key role in bringing about an efficient and fast implementation of VLSI chips that is possible with the schematic circuitry. There are, as I said, the HDLs have many advantages. Design cycle time reduces. It provides a concise representation of the design in contrast to the schematic logic diagrams. No need for minimization, all that is taken care of. Design is portable, that means I can have a design, a description, I can use one particular FPGA, and if I am not happy with that particular market vendor, I can go to another vendor and use the same description. Of course, I may have to recompile it for his design device, but it is possible. And it is technology independent. It can be as I said, 70 nanometers, or it can be 1 micrometer. I can still use it, technology independent. There are two types of language. One is called Verilog, the other is VHDL. But we will use Verilog in this course mostly. Verilog and VHDL are most popular HDLs. Using HDL, we will see that one can design digital circuits all the way from SSI. SSI is small scale integrated circuit like gates and simple one bit full adder, to VLSIs, ICs like microprocessors. Verilog will be used in this course, not the VHDL. These are both. There is a subtle difference, there is the way in which you do things. One is Verilog is more industry friendly, VHDL is in academics, and some part of the world they use Verilog, other parts VHDL. It doesn't matter really. Design methodology adopted in this course is easily applicable. So don't worry that if you are learning Verilog, VHDL cannot use. No, it's not. It's not like that. It's very, very easy. Verilog is used because it's structured like C language, shell-based structure, so it's easy. So Verilog is a hardware description language. It was used by Gateway Design Automation in 1984. Became an industry standard because of its simplicity and C-like structure. And it is popular in the west coast of the United States and with industries, whereas in VHDL is widely used in the east coast of USA and institutions. Verilog based synthesis technology was introduced by Synopsys. There is a synthesis, we will go to that. Both Verilog and VHDL are governed by IEEE standards. So we have to know synthesis. What it means is first you have to, we will have go through that. We will have to first describe and then go through a description, and then we have to compile it and then synthesize it and all that. So Synopsys is a synthesis tool which will be used. So what are the various things? Verilog allows different levels. I can describe the behavior of circuit. I can give the data flow of the circuit, or I can give a gate or structural level description. I can give an RTL. RTL means register transfer language. It is register transfer. How do you go about? Or it can also be switches, NMOS, PMOS type of thing. You can go to that level. So once you do Verilog, we will again introduce you to the Verilog properly and how to realize combination circuits, how to realize sequential circuits. Once you do that, how to code it. Once you see, realizing is just simply writing, but you have to organize the code properly for efficient design. And you have to test it. Writing a test bench is important. How do you know if your design is going to work? You cannot fabricate it every time. So you have to write what is known as a test bench. And when it works the test bench, it will work with your design finally. And then RDL coding guidelines will be given to you. Only certain things are synthesizable. You can write a behavioral description. You can simulate it in the lab. You can see it in the oscilloscope. But when you try to build it, it won't work. So what are the guidelines you need to use in order to make it synthesizable? So you should know what is the design flow that means and what is the methodology. That will be introduced to you, design flow, and then we will simulate. First of all, we will have to simulate it before you can go to plunge into the fabrication. So, simulation of Verilog, there is a tool called Model Sim, will be used along with Verilog to tell you how to use it. And then you have to synthesize it. This is what I said, synthesis is actually building the component by component, block by component by component building is called synthesis. Where behavior description is translated after the simulation of the behavior description or the Verilog simulation. You have to synthesize it, which is ready for implementation, mapping onto the FPGA. This process is called synthesis, and we will use a tool called Simplify. And we can see in this Simplify your RTL and technology view. That means you can see the schematic circuit view of the Verilog codes. So, when you do the code, it looks like a computer language, as I said, C-like structure and all that, but you should really know that finally it is what you want, an adder. You know how an adder looks like. So, when you look at this view, technology view, RTL view, you can see that in this circuit is similar to what you wanted. So, that way you are satisfied that what you are designing is what you wanted. And there will be errors, and you should know how to model sim may be error, this synthesis process also you may have errors. When errors occur, how do you handle it? Then after having synthesized it, you are ready to put it on a map it on a device, FPGA device. That means you have to place it, placing the various components within a field programmable gate array and route it. Place and route is what are the various functional blocks we are going to use within the FPGA for realizing various specifications of the required circuit, and how are you going to interconnect them, that is routing. And once you do it, you go back and see whether the back annotation. See, when you make that placing and routing, you may make some minor changes, and when you back annotate, you will go and back and verify whether your thing is still what you wanted. So, that is called back annotation. And then you have what is known as a floor plan, which are the units of the FPGA will be connected in what way. And then after doing that, we will give you several examples. We will tell you how to design memories. So, as I said, this is not going to be a simple course, it is going to be an advanced course. So, you should know how to realize memories, read-only memory, random access memory, external controller, external memory, how do you control them, controller for accessing external memories. We will design arithmetic circuits for you. We will talk about serial adders, subtractors, parallel adders, subtractors, parallel multiplier is a very common thing today in IC design. You need to know how to design multipliers. Parallel multipliers, the multiplier is very fast. Earlier they had Booth's multiplier and all that. Even before that they had serial multiplier. Serial multiplier very slow. Then they had this serial parallel multiplier, something like Booth multiplier. Now we have what are known as parallel or array multipliers. How do you design them? Design of parallel adders, subtractors, Booth multiplier, and also design of array multipliers, all that will be taught to you. And then FPGA, using this FPGA you can design any application. Many applications will be given as examples. Design of PCI arbiter, PCI control, peripheral control interface arbiter, and then we have a design of a traffic light controller. We will do a discrete cosine. Now, discrete cosine transform is used in compression video signals. These are all some of the examples. It's not complete, exhaustive. There are lots of things you can do. We can only teach you a few. Even this has run, as I said, about 50 lectures. And in everything you will be shown practically how to do it. You will be developed, the code will be developed, code will be shown to you, how to synthesize it, how to simulate it, how to use the tool, how to identify error, how to load it. Everything will be shown to you in this course. Very interesting. Design and real-time clock with stopwatch. And we will also give you several applications which can be used further. And then detailed specification of electrostatic precipitator, which is an application which you will be asked to do yourself, electrostatic precipitator control of FPGA implementation. Detailed specification of variable length coder, this is again one of those video compression, building blocks, functional units. So, this is the type of things we learn in this course. It is an exhaustive course. We'll learn. I gave an introduction of what is VLSI. Why do you need to do VLSI? I also said why we are only doing digital, because you cannot do everything, and digital is most widely used and easy to implement and understand. So, when you are doing the first time a VLSI design, you start with digital. Then if you are an expert and you become interested, you go to analog VLSI design and then mixed signal. Then we'll have to teach you a lot of things about digital design itself. You may not be completely familiar with them. Advanced level, not only advanced level, a systematic way of doing it, because your design has to be systematic if you want to implement it. So, not only it is an advanced design, it is only systematic design, and then once you have that, we introduce the description language, hardware description language, very large, how to translate your design into codes, and how to simulate the code, how to synthesize the code, how to write test benches, and then how to synthesize it, and how to map it, how do you back annotate and see whether the design is okay, how to find the errors and how to fix them. So, you will be given complete information knowledge, and at the end of this course you will be very confident in designing digital system of any description. Given the size of the FPGA under your control, to fit into that size you can design anything of interest. And as I said, we will give you several complete examples, several subsystem design like traffic controller, several full control like vending machine, and give you a list of things to do. There will be lots of exercises and problems. So, I hope you will enjoy this course, and we have an exciting syllabus for you. My colleague Dr. Ramachandran will also share the lectures. Both of us will lecture in turns. So, you will see two faces during these lectures, and at the end of it I am sure you will become a good VLSI, digital VLSI system designer. I look forward to teaching this course along with my colleague Dr. Ramachandran. The next 50 or so lectures, I hope you will have patience to bear with us in the entire period, but I am sure you can reward are well worth it. Good day.